This video is about one-sided limits and closed interval continuity. Recall that in order for the limit of f of x to exist as x approaches c, f of x must approach the same value from the left of c and from the right of c. So look at this example. Does the limit exist as x approaches 2? You know what? This function does not have a limit as x approaches 2 because the function approaches two different values from the left and from the right of 2. As x approaches 2 from the left, the function is approaching one value. As x approaches 2 from the right, the function is approaching a completely different y value. So here's where I get to introduce you to the concept of one-sided limits. As x approaches 2 from the left, f of x approaches 3. Watch this. As x approaches 2 from the left, the value of the function does approach 3. That's called a one-sided limit. We use this limit notation for a one-sided limit. Notice the negative sign right here. That's the part that means from the left. So as you read this notation, you would say the limit of f of x as x approaches negative 2 from the left is 3. There's also a one-sided limit as we approach 2 from the right. So notice, as the x values approach 2 from the right, the value of the function approaches 1. That is a one-sided limit. We use this notation right here. Once again, because the value of the function is approaching 1 from the right, we write this. And again, the plus sign right here means from the right. So we say that the limit of f of x as x approaches 2 from the right is equal to 1. That is another one-sided limit. In a previous video, we talked about the fact that a limit will only exist if the function approaches the same value from the left and from the right. In this example, as x approaches 2 from the left, the function approaches 1. As x approaches 2 from the right, the function approaches 1. It has to approach the same value from the left and right for the limit to exist. So now we can describe that same situation using our new fancy notation. So the existence of a limit. The limit of f of x as x approaches c is L if and only if the limit of the function as x approaches c from the left is equal to L, and the limit of the function as x approaches c from the right is equal to L. Basically, this is saying the same exact thing that we said in a previous video, where it has to approach the same value from the left and from the right. That's all this is saying. In order for the limit to exist, the function has to approach the same value from the left and from the right. Oh, look, right here, I went ahead and just spelled that right out for you. Let's look at a few examples. Example 1. Let's talk about the function f of x is equal to the square root of x. So here's a graph of the function square root of x. What can we say about limits as we look at this graph? First of all, let's talk about the limit as x approaches 0. First of all, we can say that the limit as x approaches 0 of the square root of x does not exist. remember, like we just said 30 seconds ago, for a limit to exist, the function has to approach the same value from the left and from the right. But the function is not defined from the left. All right, the function doesn't exist over here. So there's no way you can say that the function approaches the same value from the left and from the right when there is no left. So the limit does not exist. On the other hand, we can talk about the one-sided limit from the right. So let's talk about the limit as x approaches 0, but I'm going to put this plus sign on here to mean we're only talking about from the right. So as x approaches 0 from the right, we can see that the value of the function approaches 0. So we can say that the square root of x, the limit of the square root of x as x approaches 0 from the right is 0. So what can we say about limits when we're talking about the function f of x equals the square root of 4 minus x squared? Let's look at the graph. Well, here's a quick look at the graph of this function. Let's talk about the limit as x approaches -2. Well, look, this limit does not exist. The reason why this limit does not exist is because the function has to approach the same value from the left and from the right. But this function is not defined over here. So we can't talk about what's happening as x approaches -2 from the left. So we can't do from the left and from the right, so the limit does not exist. But now let's talk about the one-sided limit as the x values approach -2 from the right. So as the x values approach -2 from the right, the y values, or the value of the function, approaches 0. So there is this one-sided limit, and we write it this way, and we say the limit of f of x as x approaches -2 from the right, that's what the plus sign means, is 0. Similarly, the limit of f of x as x approaches 2 does not exist. And again, the reason why this does not exist is because for a limit to exist, you have to be able to say that the function approaches the same value from the left and from the right. But the function is not defined on the right. The domain ends here at +2. The function doesn't exist past +2. So because there is no from the right, the limit as x approaches 2 cannot exist. However, we can talk about the one-sided limit, the limit of the function as x approaches -2 from the left. So as x approaches -2 from the left, the value of the function approaches 0. So there is a one-sided limit from the left. So let's think about limits as we examine the greatest integer function. So first of all, what is the greatest integer function? This function basically rounds down to the first integer. So that means, first of all, if you take this function and you apply it to an integer, which is a number like 5 or -3 that has no decimal or fraction to it, if you apply the greatest integer function to an integer, nothing changes. It just gives you the integer back. So the integer function of 5 is 5. The integer function of -2 is -2. So that gives us several points on our graph right away. Because the integer function of 0 is 0. The integer function of 1 is 1. The integer function of 2 is 2. -1, -1. -2, comma, -2. Now, what about the decimals, though? Let's look at what happens between 1 and 2 just as an example. So I'm just going to draw a little line right here. And let's think of what happens at 1.1. Well, remember, the integer function rounds down to the nearest integer. So 1.1 is going to just give you 1. And that's going to keep happening. So 1.2 is going to round down to 1. 1.3 is going to round down to 1. 1.5 is going to round down to 1. 1.9 is going to round down to 1. So look how that plays out on the graph. So if I want to see what happens at 1.1, 1.5, 1.9, all of those values are going to be still at 1. So it's going to make this sort of flat curve. When I get to 2, that's when it jumps, because we know that the integer function at 2 is 2. So when I get to 2, boom, it jumps up to here. But so I get this sort of flat step happening. And if you apply that same reasoning at these other values, we're going to have a flat step right here. And we're going to have another flat step right here. And we'll have another flat step right here. So this is what the greatest integer function looks like. So here's an example of something we can say about limits. The limit of the greatest integer function as x approaches 0 does not exist. Again, for a limit to exist, it has to approach the same value from the left and from the right. So notice, as x approaches 0 from the left, we are approaching one y value. As x approaches 0 from the right, we're approaching a different y value. That's why the limit as x approaches 0 does not exist. Now, what about the limit of the greatest integer function as x approaches 0 from the left? See the little negative sign? That means from the left. So as x approaches 0 from the left, the function is approaching -1. On the other hand, as x approaches 0 from the right, the value of the function is approaching 0. We could do a similar analysis at other points, but I just want you to notice that there's a discontinuity at every integer. If I look at -1, see the jump right here. That's a discontinuity. At 0, there's a discontinuity. At 1, at 2, at every integer, there's going to be a jump. There's going to be a discontinuity. In a previous video, we learned the definition of continuity at a point. A function is continuous at c when these three conditions are met. The function has to be defined at c, the limit as x approaches c has to exist, and the limit as x approaches c has to equal the value of the function at c. So together, these three rules guarantee that there will be no break in the graph at point C. So that's continuity at a point. But we can also talk about whether or not a function is continuous on an interval. Some intervals are open intervals, like this one. An open interval just means that the endpoints are not included. So This is a picture of the open interval a, b. We use this notation with parentheses. That means it's an open interval. That means a and b are not included. But other intervals are closed intervals, like this one. This is a closed interval from a to b. That just means that the endpoints are included, and we write the interval this way with brackets to show that the endpoints are included. So the definition of continuity on an open interval is really straightforward. We just talked about continuity at a point. So if a function is going to be continuous on an open interval, it simply has to be continuous at every point along the interval. So by that definition, you can see that this function is continuous on the open interval from a to b because it is continuous at every point between a and b. Pick any point and it's going to satisfy the three conditions. But what about the closed interval from a to b? Is the function continuous at every point on this closed interval? Actually, no. The problem is the endpoints. The function is not continuous, for example, at point A, because it fails the second condition, which says that the limit has to exist at that particular point. And the limit does not exist at point A, because for a limit to exist, the function has to approach the same value from the left and from the right. Well, look, you can approach A from the right, but you can't approach it from the left. The function doesn't exist over here. So the limit doesn't exist, so the function is not continuous at point A. Similarly, the function is not continuous at point B. You can approach point B from the left, but you cannot approach it from the right. It doesn't exist on the right. So the function is not continuous at point B. So by this definition, this function would not be considered continuous on the closed interval from a to b, even though this is a lovely, unbroken piece of function. So if we want a function like this to be considered continuous on the closed interval ab, we're going to have to modify this definition a little bit. So first of all, if a function is to be continuous on closed interval ab, first of all, the function has to be continuous at every point on the open interval ab. In other words, ignoring the endpoints, the function has to be continuous between a and b. Now, when it comes to the endpoints, we're going to be satisfied with a one-sided limit. For example, the limit as x approaches a from the right simply has to equal the value of the function at a. In other words, as we approach a from the right, the value that the function is approaching has to be the same as the value of the function at a. In other words, it can't do this. It can't be approaching one value as we approach a from the right, and then at a, it's another value. That can't happen. And we say that f of x is continuous from the right at a. Similarly, at b, we're going to accept a one-sided limit. The limit as x approaches b from the left has to equal the value of the function at b. Again, that just means that as we approach b from the left, the value that the function is approaching has to be the same as the value of the function at b. In other words, it can't be doing this. And we can say that f of x is continuous from the left at b. So clearly, this function would not be continuous on the closed interval ab. So let's revisit a couple of examples from before, this time considering continuity on an interval. So we would say that this function is continuous on the closed interval from -2 to +2. But if we wanted to go into a little bit more detail analytically, we would say that yes, the function is continuous on the open interval from -2 to +2, meaning it's continuous at every point between the two endpoints. But then at the endpoints, we need to consider the one-sided limits and show that they are equal to the value of the function at the endpoint. So specifically, look at the limit as x approaches -2 from the right. So as the x values approach -2 from the right, the value of the function is approaching 0. Now let's compare that to the value of the function at -2. So what is f at -2? Well, just looking at the graph, we can see that the value of the function at -2 is 0. Or if we use the equation, if we substituted -2 in for x right here, again, we would get 0. But what matters is that these two values are the same. So similarly, on the right-hand side, let's look at the limit as x approaches +2 from the left. So as the x values approach +2 from the left, again, the value of the function is approaching 0. Now let's compare that to the value of the function at the endpoint and see if they're the same. So if you wanted to trust the graph, you can see that the value of the function at the endpoint is right here, again at 0. And again, if we substituted +2 into the function for x, we would get 0. And what matters is that these are the same. So we have shown analytically that f of x is continuous on the interval, the closed interval from -2 to +2. Let's finish with an example that's a little bit different. Take a look at this graph of the square root of x. Clearly, this function is continuous throughout its domain. It is unbroken. However, the domain of this function is from 0 to infinity. This is neither an open interval nor a closed interval. So what are we going to do? We could say that f of x is continuous on the infinite interval from 0 to infinity. Now, if we wanted to prove this analytically, we would have to take a closer look at the endpoint. Notice that the 0 is included. It's closed on this side of the interval. So when you're dealing with an endpoint, you're going to have to look at the one-sided limit. So the limit as x approaches 0 from the right. What is it? So notice as x approaches 0 from the right, the value of the function approaches 0. Now let's take a look at the value of the function at the endpoint, the value of the function at 0. Well, we can either look at it graphically and see that the value of the function at 0 is 0, or we can imagine substituting 0 in for x, and we would get a value of 0. The important thing is that these are the same. So that's how you would show analytically that f of x is continuous on the infinite interval from 0 to infinity.